Okay, the first part is on the introduction to sufficient statistics. So actually, the first step tu kita just review back on the measure of quality of estimator. So actually this one, we already looked at the concept for properties for unbiased estimator. Okay, unbiased estimator, that means if you have a theta head, so you need to prove expected value of theta head is equals to theta. And then we proceed with consistent estimator. So consistent estimator is when we have a large sample, so kau punya n approaching infinity lah. So dia akan consistent sama ada dia converge into probability. Okay. So that's mean if the value for your estimator is converged, okay, into the probability, so it will become a consistent estimator bila kita ada n approaching infinity, okay, for large sample size. Okay, and then the third one is for efficient estimator. So efficient estimator, normally you compare your variance, okay, variance theta 1 and also variance theta 2. So which one is more efficient? So what we have before this is the concept uniformly minimum variance unbiased estimator. So that is the three quality of estimator. But what we emphasize before this is just on unbiased estimator and also efficient estimator. Okay, itu yang saya dah bincang dalam previous punya lecture lah ya. Okay. So again, the concept now is on the sufficiency. So sufficiency, we call that one is a sufficient statistic. Okay, so we have several kind of statistic, but again, in your syllabus, we only emphasize on sufficient statistic and also complete sufficient statistic. Okay, if you look at any reference textbook, okay, there is also a term called ancillary statistic. Itu pun ada. Okay. But cuma in your syllabus, we only emphasize sufficient statistic and also complete sufficient statistic. Okay. So ini saya harap kamu dah tengoklah dia punya video tu. Okay. So ini just kita repeat baliklah a little bit on sufficient punya concept. So actually we have this kind of statistic. So this statistic is a function of a random sample. Okay. So let's say we denote this statistic as a function t here. Okay. So t is equals to u x1, x2, xn. So it is a function of the random sample. Okay. Normally if you have a set of your observation, okay, kita ada x1, x2, xn. So apa yang kita buat? Kita listkan all the values. Okay. And then we take sample mean or sample variance to express the information that contained in the sample. Okay. For example, your x bar is summation xi over n. And then we compute your sample variance. Okay. So let's say statistic T, okay, is a form of data reduction. Okay. So that means normally statisticians look for ways of reducing a set of data so that this data can be more easily understood without losing the meaning. So instead of kita listkan semua observation, okay, so what we need here is just represent it in terms of your x bar or your sample variance. So katakan x bar dia 3.5. So secara overallnya, secara puratanya, that your punya list of observation mempunyai nilai secara average-nya lebih kurang 3.5. Okay, itu secara puratanya. So instead of kita listkan setiap observation, especially when we have a large sample size. So normally what we do is we try to express it in terms of another statistic where we call this one as sufficient statistic. Either it can be in terms of your mean or your sample variance. It depends on the questions. Okay. So this is definition for sufficient statistic. So T is a sufficient statistic if the statistician who knows the value of T can do just as good in estimating the unknown parameter theta as the statistician who knows the entire random sample. So instead of kita ada semua observation, kita expresskanlah, okay, dalam bentuk kita punya sufficient statistic. Okay. Formally, a statistic T, okay, which is a function x1, x2, xn, is said to be sufficient for theta if we have the conditional distribution. Okay, conditional distribution of x1, x2, xn given t. So maksudnya it can be written as probability x1, x2, xn given t. Okay, this conditional distribution does not depend on theta for any value of t. Okay, untuk t, kita punya t tu sufficient statistic kita. Okay, t tu does not depend on theta for any conditional distribution lah. Kita ada conditional distribution, probability x1, x2, xn given t does not depend upon theta. So in other words, given the value of t, we can gain no more knowledge about theta from knowing more about the probability distribution of x1, x2, xn. Okay, so let's say we can only keep t and then throw all the observation lah without losing any information. So apa-apa pun kita boleh expresskan dalam bentuk sufficient statistic. Okay, so that is enough for us to represent it ataupun to express lah dia punya value in terms of the statistics. Okay, so this is the definition. So just now we have the conditional probability. So if we remember back the conditional probability, the concept is, let's say if we have A and B, so probability A intersect with B divided by probability of B. Okay, this one So T is a sufficient statistic. Kalau kita expresskan tadi, kita dah ada this one S1, S2, SNT. So kalau kita ada fs1, fx2, fsnt, okay ni So again, tadi x1, x2, so ini p, xn given p. So kalau kita open dia punya bracket dia ataupun open dia punya conditional probability dia, so it becomes fx1, fx2, fsn theta divided by probability of t ni, which is denoted as gt theta. So kalau let's say if you get conditional probability, so let's say we denote sebagai h x1, x2, xn does not depend upon theta. So in this case, your t is called as sufficient statistic. Kalau kita buat conditional probability so this one fs1, x2, xn given t. So expresskan, okay, this is the join PDF dia fx1, fx2, fsn divide by PDF of T distribution tadi. Okay, T sufficient statistic ni. So kalau kita ada this one, so you get the conditional probability which is H, x1, x2, xn does not depend upon theta. Maksudnya dalam H tu tak ada nilai theta. So then we call T as a sufficient statistic. Okay, maksudnya dia hanya depend pada T je. Dia tak depend pada parameter theta tadi. Okay, bila punya conditional probability dia. So if we have this kind of expression lah kita mahu ada conditional probability dia. So and then you get conditional probability does not depend upon theta. So then we can call that one T is a sufficient statistic. Okay, kita expresskan dalam bentuk ni lah join PDF ni. Okay. So contoh yang diberi dalam video tersebut adalah Bernoulli trial So kalau Bernoulli trial, you have theta to the power x, 1 minus theta, 1 minus x. Okay. You want to show that t equals to summation xi is a sufficient statistic. Okay. We use the concept of conditional probability. So this is the concept. Okay. This one So again, here we assume that your random sample are independent. So by independence, we get the joint distribution, this one. So kita ada fs1 theta, fx2 theta, fsn theta. So we have here is theta xi, 1 minus theta to the power 1 minus xi. So simplify form there, you get this one. Okay. Sebab kita expand lah setiap satu tu. Theta s1, 1 minus theta, 1 minus x1. Theta x2, 1 minus theta, 1 minus x2. Simplify kan, you have this term. Okay. So T sekarang adalah summation xi. Okay, T adalah summation xi. Okay. So kalau kita ada probability x1, x2, xn and then also T equals to T. Kalau kita open bracket ni kita ada inilah probability A intersect with B. So since they are independent, so x1, x2, xn and T equals to T. Okay. So you have x1, x2, xn minus 1. Katakan kita ungkap xn kita sebagai T sebab T tadi adalah summation xi. Okay, minus summation si from I equals to 1 up to n minus 1. Okay, kita dapat balik Sn lah. Maksudnya kat sini kita, we will have x1, x2 plus xn. Okay, yang ni, x1 plus x2 plus xn minus 1. Okay, so this is your t. Okay, so t minus this one, you get back your value for your xn. Okay, so that's why kita dapat this one term dia. Okay, that one Okay, then since the random sample are independent, okay, independent you can multiply the probability. Okay, so kita dah ada this one. Okay, theta x1, theta x2, and then theta t. T kita dah tahu summation xi. Okay, minus summation si from I equals to 1 up to n minus 1 and so on. Okay, bila kita simplify kan, kamu akan dapat this term. Okay, sebab ini summation I equals to 1 up to n minus 1, kita dah cancel out ni. Okay, sebab last term kita akan ada theta Sn minus 1, 1 minus theta, 1 minus xn minus 1. So ini semua kamu dah total up, so it's cancelled by this one. Okay, so kita ada 1, 1, 1, 1 minus x1, so kita ada n terms. Okay, so itu pun kita dah cancel up, so yang tinggal adalah theta to the power t, 1 minus theta, n minus t. Okay, so ini dah cancel out dengan this one, x1, x2, xn minus 1. So tinggal theta t je. Okay, next you have 1 minus theta, 1 minus t minus summation si. Okay, so again kita ada 1 minus t, 1 minus, 1 minus sebanyak n terms, so that's why kita ada n. Okay, minus ini pun dah cancel out dengan minus x1, minus x2 and so on, so cancel out, so kita ada n minus t. Okay, so that is your value. Okay, so we know that t equals to summation si has the binomial distribution. Kita ada binomial distribution. Yang asal tadi is a Bernoulli trial. So Bernoulli trial, kalau kita ada n random sample, kita ada summation, it becomes binomial distribution. So that's why kita ada PDF for t distribution. Okay, summation si ni. Kita ada in terms of binomial probability distribution, which is n choose t, theta to the power t, 1 minus theta, n minus t. Okay, t from 0 up to n. So sekarang conditional probability, ini kita dah selesaikan yang tadi. Okay, PDF for t, which is binomial distribution, so you replace, so you cancel out this one, and also this one, kita dapat ini. So this is your h, x1, x2, Sn, which does not depend on the parameter theta. Okay, dia bebas daripada theta. Okay, so by definition, t equals to summation si is a sufficient statistic. Okay, itu cara macam mana kita tunjukkan dia adalah sufficient statistic. Okay, kita dapat PDF for t because asalnya your x1, x2, xn is a Bernoulli. So when we have the summation, it will become binomial distribution. Okay, so you have n, choose t. So theta, parameter dia, theta to the power t, 1 minus t, n minus t. So cancel out this, letakkan dalam bentuk conditional. So cancel out, you get 1 over n choose t, which is your function for h, which is does not depend on parameter theta. So by definition, t is equals to, ataupun t equals to summation si is a sufficient statistic. Okay, so that one apa yang dah diterangkan dululah dalam kita punya ni. Okay, so itu konsep sufficient statistic. So the same thing, kita cuba buat the next one. So this is a Poisson distribution. Okay, sama juga, kita nak show that t is equals to summation si is a sufficient statistic for lambda. Okay, so kita akan guna definition for sufficient statistic. Okay, definition, so that's mean kena apply conditional probability dia lah, which is kamu dah ada probability x1, x2, Sn equals to Sn given T. So ini dia punya by definition. Okay, definition of sufficient statistic. So the same thing, you have Poisson distribution. So kalau kita ada join PDF, okay, the join PDF, X1, X2, Sn, which is coming from Poisson distribution. So kita ada I equals to 1 to N, Fxi, parameter lambda. Okay. And then you will have exponential negative lambda, lambda x1 over x1 factorial, exponential negative lambda, lambda x2 over x2 factorial, then exponential negative lambda, lambda xn over xn factorial. Okay, so here, okay, so kalau kita simplify kan, kita ada di sebelah, kita ada exponential negative n lambda, dan summation xi, product of xi factorial. Okay, tapi sekarang ni kita nak bentukkan dalam bentuk conditional probability. Okay, kita nak bentukkan dalam bentuk conditional probability. Okay, so you will have probability x1, x2, and then you will have xn equals to xn given t. Okay. Then kita open dia punya bracket so you will have x1, x2, okay, and then xn minus 1, xn minus 1, and then for xn is equals to t minus summation xi, I equals to 1 up to n minus 1, this one. Okay, divide by probability t equals to t. Yeah, so di sini saya letakkan probability x1 equals to x1, x2 equals to x2, xn minus 1 equals to xn minus 1. Xn ni saya ungkapkan dalam bentuk t sebab t tadi adalah summation si minus summation si from I equals to 1 up to n minus 1. So actually dia dapat baliklah Sn. Okay, divide by probability t equals to t. Yeah. So now kita gantikan dia punya nilai probability dia. So that's mean you will have exponential negative lambda, lambda x1, x1 factorial, exponential negative lambda, lambda x2, x2 factorial. Okay. Kat sini kita ada exponential negative lambda. Okay. Untuk lambda Sn, dia akan jadi lambda t minus summation si, tapi I equals to 1 up to n minus 1 over t. Sorry, I equals to 1 up to n minus 1. Divide. Okay, sekarang kita nak dapatkan probability t equals to t. Yeah. So t is equal to summation xi. Okay. So setiap satu tu x1 is Poisson lambda. x2 pun Poisson lambda. Sn pun kita ada Poisson lambda. Sekarang ni kalau let's say if you have t equals to summation si. Okay. Saya tulis dulu probability t equals to t. So kalau probability t equals to t, okay, which is t is equals to summation si. Yeah. It will become exponential negative n lambda to the power t over t factorial. Okay. Itu kalau kita ada t equals to summation xi. Okay. Sebab let's say if you have expected value of t, katakan kita tak tahu apa dia punya probability mass function for T equal to summation Xi. So expected value of T adalah expected value of summation Xi. So bila kamu expand summation Xi, you will have X1 plus X2 plus Sn. Ni. X1 plus X2 apalah plus Sn. Okay. Setiap satu tu EX1 dia lambda, EX2 dia lambda, ESN pun lambda. So kamu ada N lambda. Okay, N lambda. So kita dah ada dia punya parameter dia, which is N lambda. So untuk probability T equal to T, probability mass function dia akan jadi exponential negative N lambda to the power T over T factorial. Okay, so itu adalah dia punya PDF of your T distribution tadi. Okay, ataupun T random variable lah. Okay, PDF for T random variable. Okay, mana T tu adalah summation Xi. Okay, macam mana saya dapat N lambda? Sebab kita ada expected value setiap satu adalah lambda. So, sekarang kita nak dapatkan expected value of summation Xi. So, you will get your N lambda. So, this is your parameter. So, masukkan balik dalam probability mass function for Poisson. Kita ada exponential iaitu N lambda to the power T over T factorial. Okay. Sebab kalau Poisson, random variable, kalau X pun Poisson, X2 pun Poisson, summation Xi pun still Poisson distribution. But again, if that one is Bernoulli, okay, Bernoulli triad dia 0 and 1, X1 Bernoulli, X2 Bernoulli, tapi kalau summation dia akan jadi binomial distribution. Okay, itu you have to remember lah. Kalau Poisson, still Poisson lah. So this is the probability mass function. Okay, now kita substitute balik dalam kita punya conditional probability. Okay, substitute back in the conditional probability. So kita dah ada Xi given T. We already have the conditional probability. Exponential negative lambda x1 over x1 factorial. And then exponential negative lambda x2 over x2 factorial. And kita ada exponential negative lambda t minus summation I equals to 1 up to n minus 1. And then instead of xn, kita ada t minus summation I. Okay. Divide by exponential negative n lambda to the power t over t factorial. Okay. So exponential negative lambda, kita ada n terms, so kita ada exponential negative n lambda, so itu cancel out. Okay. And then what we have here is just this one lah . So kita ada okay, cuba kamu simplify kan. Cek dengan jawapan saya, kita ada t factorial. Okay. And then you have n to the power t. Okay, n to the power t. And then product I equals to 1 up to n. Okay. And then this one lah. Ada this one t minus. Okay, so that one Okay, so kita dah cancel I exponential negative n lambda. So kamu ada here adalah exponential negative lambda. Okay. So exponential negative lambda. So kita ada semua exponential negative n lambda. So cancel out dengan this one. Okay. Lambda S1, lambda ni. Okay, so you tinggal adalah lambda t So lambda t cancel out dengan lambda t here. Okay. So yang tinggal adalah n over t je here. Ini t factorial dengan distance dia. Okay. Okay, ada apa-apa soalan kah? So that's mean this one by definition, this does not depend upon lambda. So ini kiranya kita tak ada nilai lambda dah. So that's mean your conditional probability here is x1, x2, xn. Okay. So since your is x1, x2, xn does not depend on lambda. Okay. So t equals to summation xi is a sufficient statistic. Okay. Okay, so itu menggunakan kaedah definisi definition dia. Okay, ini gunakan kaedah definition for sufficient statistic. Okay, di mana kita ada conditional probability. So conditional probability, so kalau let's say if we can prove that your conditional probability does not depend on the parameter theta, so by definition your T is a sufficient statistic. Okay, tapi kita juga ada approach dia which is we use the theorem. Okay, a simple way how we can get the sufficient statistic. Ini kaedah yang panjang. Okay, cara yang panjang di mana kita gunakan kaedah conditional probability function before we came out with a theorem. Okay. So ini untuk Poisson distribution sama juga kaedah dia macam untuk binomial distribution tadi. Okay. So for simple way, we use another theorem where we call this one as factorization theorem. Okay, factorization theorem. Okay, as I stop sharing this one, so we go to the other parts, okay, which is much more easier to understand. So this one is a factorization theorem. Okay, so ini kita panggil sebagai theorem 2.1, Fisher-Neyman factorization theorem. Okay, so kalau yang tadi tu kita kena dapatkan dia punya probability function for your ataupun probability distribution for your sufficient statistic tadi. So that's why the question asks you show that T equals to summation SI is a sufficient statistic. Okay, sebab dia dah ada T equals to summation SI, so kita dah tahu kita nak dapatkan family distribution dia untuk summation XI. Okay, but when we apply for Fisher-Neyman factorization theorem, normally the question set is find the sufficient statistic. Okay, sebab kita tak perlu lagi dapatkan PDF for your sufficient statistic. So we use this theorem. So this is by Fisher and Neyman factorization theorem. So again, if we refer to this theorem, you have a statistic T. So T ni kita denote sebagai sufficient statistic. Okay. If and only if the joint PDF dia, okay, joint PDF of the XI may be written as follows. So that means fs1 theta, fx2 theta, fsn theta. Tapi kita boleh ungkapkan dalam bentuk gt theta, h x1, x2, xn, where your function h here does not depend upon theta. Okay. So kalau kita boleh splitkan kita punya joint PDF into two parts. The first part, dia depends on theta lah. Ini ada theta, gt theta. The second part does not depend upon theta. So then we can call that your T is a sufficient statistic. Okay, kita tak perlu lagi buat conditional probability function. Okay. Okay, note that to use factorization theorem to find a sufficient statistic, we factor out the joint PDF into two parts. Okay, first part not depend on theta, the other part is depending on theta lah. So the part yang does not depend on theta tu biasanya kita letaklah dalam simbol HX. Okay, so the other part, the one that depends on theta, usually also depend on the sample X. Okay. Only through some function, and this function is a sufficient statistic. Okay, yang first part yang tak depends on theta, kita ada fungsi H dia tak ada theta. Okay. Tapi the other part ada theta, and then dia punya sampel X tu mesti ada X lah, X1, X2, Xn. Dia ada dalam bentuk fungsi X. Okay. Then this function is called as a sufficient statistic for theta. Okay. Nanti saya tunjuk dia macam mana dia punya contoh dia. Okay. So ini just dia punya notes ni. So one writes out the joint PDF of the xi and then try to rewrite it as a product of two factors. Okay. One depends on theta, the other one does not depend on theta. So kalau function g ni, okay, contains the xi only through the function, okay, and the parameter theta. And another factor h ni which involves only x saja, tapi tak ada theta. Okay, satu function dia ada x, dia ada theta. Okay, satu lagi fungsi h tak ada langsung theta, dia ada x sahaja. Okay, so that one. Okay, the other one, theta head is sufficient for theta. Then any one-to-one function, for example, let's say lah kita ada constant. Katakan k theta head ataupun theta head plus k. So ini pun akan jadi sufficient statistic for theta. So katakan x bar is a sufficient statistic. So katakan x bar plus 2. So it also a sufficient statistic. 2x bar also a sufficient statistic. Okay, ini yang notes yang kedua. Okay, yang dia punya ni kx lah, tak kisahlah, constant value. Okay, any value. Okay, that one. Okay, apa that one lah. Okay. So macam mana kita nak tentukan dia adalah sufficient statistic? Okay, so katakan kita nak dapatkan dia punya theta head. So ini dah bagi hint, show that theta head x1, x2, xn is a sufficient statistic for theta. Okay, kita punya produk ni. Okay, first part, you write down your joint PDF. First step, kita tulis dulu apa dia punya joint PDF for x1, x2, xn. So you already have fx theta. Okay, joint PDF you already learn. In order for you to derive your MLE, kita dah tulis like, dalam bentuk likelihood function lah. Kita ada fx product, fxi theta. So it's the same thing. Kita tulis dalam bentuk joint PDF. Okay. So that means you will have product I equals to 1 up to n f xi theta. Okay. So that means you will have theta, kalau kita cari panjang, theta x1, theta minus 1, multiply theta x2, theta minus 1, and then you have theta xn, theta minus 1. Okay, kita simplifikan. Kita ada theta n, product xi, and then theta minus 1. Okay. Yeah, this one. Okay, kamu simplifikan, kita dah dapatkan joint PDF, so theta to the power n, bukannya n theta, theta to the power n. Okay, x1 to the power theta minus 1, x2 to the power theta minus 1. So you will have product si to the power theta minus 1. Okay, so sekarang ni kita nak splitkan into two parts. Okay, the first part depends on theta. The other part does not depend upon theta. Okay, tapi mesti ada x dengan theta. Okay, so kalau kita tengok this one, you have theta n. Kalau saya pecahkan, product xi to the power theta. So saya ada this one, right? Okay. So kamu ada theta to the power n, product xi to the power theta, and then 1 over product xi. Right? Yeah. Okay, so now kita dah splitkan. Okay, by factorization theorem. Yang mana satu depends on theta, yang mana satu does not depends on theta. So by factorization theorem, okay, ini kita punya G, katakan saya pakai T theta. Ini kita punya H X. Okay, so by factorization theorem, FT, by factorization theorem, your hx, which is 1 over product xi, samalah x1, x2, xn. Ataupun nak simplify, just tulis product xi equals to 1 up to n. Okay, hx does not depend upon theta. Okay, so then apa dia punya sufficient statistic dia? So gt theta yang ada x. Okay, so then t equals to product xi. Okay, ataupun x1 to Sn is a sufficient statistic for. Okay, we already split this one into two parts. Okay, the first part is depend on theta. The other parts yang tak ada nilai theta. So yang tak ada theta ini je. Okay, ini kita ada theta. So kita tak boleh sekalikan. So kita boleh sekalikan dengan this one lah, theta n product xi to the power theta. So kita nak gt theta. So apa dia punya t tu? T tu kalau kita go back kepada dia punya definition dia. Yeah. Okay, t a function. Okay, a function of x1, x2, Sn. Okay. Okay, this one. The other part, the one that depends on theta, usually depends on the sample x. Only choose some function, and this function is sufficient statistic for theta. So in this case, your t is your product xi is a sufficient statistic for theta. Kita tak tulis t equals to product xi to the power theta. Tak ada Kita just tulis, kita ambil yang x dia tu saja. Yeah. So t is equals to this one is a sufficient statistic for theta. Okay, menggunakan factorization theorem. Okay, ada apa-apa persoalan kah? Boleh? So this one menggunakan kaedah factorization theorem, maksudnya kamu dah ada join PDF and then you split into two parts. Okay, first part yang ada theta, second part tu yang tak depends on theta. Tapi first part yang depends on theta tu mesti dalam bentuk fungsi x lah, dia ada x1, x2, Sn lah ya. Okay, either it can be a product, either it can be summation Si. Summation Si square is depend on your density function. Apa dia punya probability density function dia. Okay, we just apply menggunakan kaedah factorization theorem. Okay, so yang previous tadi, yang by definition tu menggunakan kaedah definisi. So kalau kaedah definition, we build up your conditional probability. Tetapi when we build up your conditional probability, you need to know what is your PDF of your sufficient statistic. Okay, kalau untuk distribution macam tadi bernuli ke binomial Poisson distribution is okay. Okay, tapi kalau soalan ini density function, kita tak tahu soalan ni fungsi apa. Kita tahu dia adalah continuous function. Tapi kita tak tahu apa family for sufficient statistic dia, apa dia punya PDF dia. So that's why we use here is the factorization theorem. Okay, untuk dapatkan dia adalah sufficient statistic lah. Which part is your sufficient statistic? So in this case, your product Xi is a sufficient statistic for theta. Okay, so dalam jalan kerja kamu kena tunjuklah kamu punya join PDF and then how you split into two parts, which is your function gt theta and yang mana satu lagi fungsi dia hx. Okay, since your hx does not depend upon theta, then you can conclude that your product Xi is a sufficient statistic. Okay, ada soalan? Boleh? Okay, kita try the other one. Okay. Solution tadi Okay, kita try this one. Exercise 2.3. Nota saya dah upload kan dalam e-learning kan, this one. Okay, you want to determine the sufficient statistic for theta. Okay, cuba dulu buat part A. Cuba you expand your punya join PDF dulu. Okay, first step, expand your join PDF. Okay, so cuba kamu expandkan kita punya fx theta. So you have theta divided by x to the power theta plus 1. Okay, dapatkan dia punya join PDF dia. Dalam bentuk macam mana kita dapat tu? So kita ada the first one here. Kamu dah ada this one I equals to 1 up to n f xi theta. Okay, so kalau kita, if you're not sure, you just expand dulu setiap satu variable tu and then you simplify. Okay, so ini kalau kita dah simplify, you should get theta to the power n bukannya n theta theta to the power n, and then you have your product here, xi theta plus 1. Okay, kita ada produk xi theta plus 1. Okay, dapat tak dalam bentuk macam ni? Okay, first step tu ini dah kena betul dulu. Kalau ada salah in terms of simplify, memang tak dapat buat lah. Tak dapat selesaikan lah apa dia punya factorization theorem. Okay, so now you split into two parts. Okay, yang ada theta kita sekalikan, yang tak ada theta letak tepi. Okay, you have that one. Right? Okay, ini kamu tulis je. So katakanlah kamu buat macam ni. So this is your G T theta. This is your HX. Okay. Lepas tu, write down a little bit. So since your HX, which is 1 over product XI, does not depend upon theta. Okay. Then by factorization theorem, okay, T dia apa sekarang ni? Produk XI ke 1 over produk XI is a sufficient statistic for theta. Kamu nak tulis macam mana? Ini theta to the power n over produk XI to the power theta. So your T should be apa? Produk XI ke 1 over produk XI?
1 over.
1 over Okay, sebab dia kat bawah Kalau yang tadi, yang ni lah yang tadi, ini kat atas. So that's why yang punya produk ini yang sufficient statistic. Kalau yang ni kita ada this one lah. So you will have T equals here is 1 over product XI is a sufficient statistic. Tuliskan dia punya justification, dia punya reasoning dia kenapa. Since our HX 1 over product XI does not depend upon theta. So ini kita dah tahu, ini kita punya HX. Then by factorization theorem, your T, which is 1 over product XI, is a sufficient statistic for theta. Okay, you already get that one. Okay, try part B. Simple je. Expresskan in terms of your joint PDF and then split into two. Okay, so part yang kedua tu, fx theta, x over theta, exponential negative x square over 2 theta. Okay. So this one pun, again, the same thing here. So you just use the product, join PDF there. Okay. So that's mean here you have I equals to 1 up to n xi theta. So bila kita simplify tu, okay, so you will have exponential negative summation xi square, okay, over 2 theta. And then this one, so you have xi, okay, theta. So ini dia akan jadi theta to the power n, and then product xi. Nampak ke? Okay, so kamu ada x over theta, okay, x1 over theta, x2 over theta, xn, so product xi. Yang tadi theta, theta to the power n, exponential ke atas kuasa, dia akan jadi summation, negative summation xi square over 2 theta. Okay, so ini pun dah siap dalam bentuk, so gt theta, this is your hx. Okay, so your hx does not depend upon theta. So sekarang t kamu apa? What is your sufficient statistic? Apa dia punya sufficient statistic dia?
Yang eksponen tu.
Ya betul, eksponen tu, tapi kita tak ambil semua. Kita ambil t is equals to summation xi square. Okay? Tak perlu ambil negative summation xi square over 2 theta Sebab kita nak function of x1, x2, xn saja. So dalam kes ni adalah summation xi square. Negatif pun tak nak. Okay? So itu kau punya sufficient statistic. Okay. Sebab kadang-kadang you punya apa? You all punya ni dah betul, cuma cara you all tulis t tu tak kena. Okay? So kalau ini kita tak ambil semua, kita ambil t equals to summation xi square saja. Okay? Tapi let's say lah if you want to take t equals to summation xi square over 2 pun diterima jugalah. Okay? Sebab 2 tu constant, tak ada apa-apa. Okay? Jangan tulis 2 theta sudah. Okay? So t is equals to summation xi square in this case. So that is your sufficient statistic. Ya? So itu dua cara ya. So kaedah pertama tadi ada secara definasi, okay, menggunakan conditional probability. So ini kaedah dia menggunakan kaedah factorization theorem. Okay?